the title that was given to me was Overview of Electronic Structure, Wave Function Based Electronic Structure Method. I still remember that. And I told Soman that is probably not right. You are doing DFT workshop. Suddenly in the evening lecture, you are changing completely to wave function based. So I changed the topic a little bit. Convert, no, so yeah. So I want to say how is DFT compared to electronic structure methods, which are very, very accurate method. There will be some references, citations, a little bit of history. So I want to make a disclaimer that if there is some error, and of course there will be lots of acknowledgement from several sources, and I will not talk much about personal accounts because we started on a day when there was no computer, and I think all of us saw those days, and today people are clicking button and doing proteins and so on, which is unimaginable at one time. I also wanted to say that very recently I gave a NPTEL Plus workshop on DFT in computational chemistry. So just I want to tell the audience that I'm not totally non-DFT person. So this was a completely DFT workshop in computational chemistry. So I wanted to show this. This was an NPTEL Plus workshop. Some of you I know have had registered and attended this. I also took NPTEL workshop on ab initio computational chemistry, hands-on session, Gaussian and so on. So I also want to first put a disclaimer that theory and computation are slightly different. Though they often are confused as the same thing, theoretical chemistry is different from computational chemistry in the sense that theoretical chemistry is examination of theories, developing new theories, and computational chemistry is when something is well developed to apply them. So many more people are doing computational chemistry than theoretical chemistry. This I can definitely tell without having a head count. So I don't need a head count for that. There's a gross disparity. When we started, it was other way around. In India, at least, there are a handful of people who used to do theory, and very few people are doing computational because that idea of computation was not there, computer was not there, where to apply, people were not sure, and very handful of people are doing theory. But today, entire thing has changed. So I think such workshops probably are very meaningful today to bring people back to theoretical chemistry. So I have defined theoretical chemistry in some way. Now this definition, of course, depends on how you want to define, but it is basically a mathematical description of physics involved in chemistry. It's very hard to put mathematics, physics, and chemistry all three together, and I just tried to do that, whereas computational chemistry is the mathematical method which is sufficiently well developed that you can now automate for implementation on a computer and actually solve proper problems. Often, I must say, the theoretical chemists also develop their own programs, codes. So in between these two are the people who develop codes. So lots of good codes have been developed, and with those developments, today chemists are using computational chemistry for several purposes. So you have seen in all interviews and so on, people look at nitrogen to ammonia, carbon dioxide reduction, and so on. I mean, I just gave some potpourri of problems, challenges, which all can be solved by computational chemistry today. At least you can give a good lead, though the experiment has to be done to eventually get it. Even environmental chemistry, hydrogen storage, certainly I myself am doing on 2 or 3 of them, these problems as an application area. So many of us are doing that. But basic idea is that computational chemistry is providing insight, and that is what you have seen. I will not go to this. The important thing is computational chemistry also provides you a structure, dynamics, and the reactivity. In fact, reactivity have different meaning. Tomorrow we will talk about chemical reactivity in terms of density, which is more qualitative, semi-quantitative. But reactivity can simply mean very accurate quantitative reactivity, like to see whether it reacts, what is the energy of reaction, everything today we can do. And in fact, biology is very similar, I must say, computational biology, except that you have a sequencing over structure, and reactivity is sometimes just called function, evaluation. So computational chemistry and biology are very well developed. Although you will very quickly see that the methods that are used are vastly different, are very often different. You can use some of the chemistry methods to biology, but they do not work well because the system sizes are very large in biology. Yes.
How about adding computation in condensed matter also?
That I am putting it under material science, computational material science. Yes, I mean agree. Probably it's an arm of chemistry also today.
Yeah, that's what
computational chemistry is merged together. But biology we use something different methods, like the molecular mechanics.
Yeah, because with chemistry then you should add that because people don't necessarily delineate between
Yeah, the biology, the problem is that it's very large systems, so you have to use MD or even mesoscopic simulation, where basically atom-atom interactions or a group of atoms interacting with another group of atoms. So that basically becomes the biological length scale, and this is a length scale where chemistry is used, and chemistry, quantum mechanics is used, quantum chemistry. Interestingly, chemistry entirely belongs to this region. And this is what I want to first tell you, that as a chemist, if you say I don't want to learn quantum mechanics, it is completely wrong. Because your molecules are at a length scale where quantum mechanics is prevalent. If you are doing biology, you can ignore quantum mechanics, but not as a chemist. And unfortunately, that is what is happening, that the chemists are very often ignoring quantum mechanics, the synthetic chemist at least. But any insight of chemistry would really come from quantum mechanics, because if you look at the lengths of the molecules, they are actually in the quantum domain, although there is a slight overlap between the domains, but it is a rough picture that holds good today, and that gives you a multi-scale hierarchy of modeling. Yeah, sorry. So basically we have been discussing this today, that what is quantum mechanics, and I will strictly talk about only the first part, because that is our subject here, is the ab initio quantum mechanics, where we solve essentially the time-dependent Schrodinger equation, but in a time-independent domain, and that gives you a more familiar Schrodinger equation of A psi equal to E psi. But remember that these are molecular mechanics or coarse graining, and people are also doing empirical, statistical like QSAR and all that for drugs. All of that together actually is a toolbox of computational chemistry. So I just want to remind you that this is not the only part, but our focus will be on the quantum chemistry. Since we are talking about ab initio methods, I will define what is ab initio, but let me first say that ab initio method, if in a typical computing setup I can do 100 atoms, within DFT one can go to 1000 atoms in the same setup, semi-empirical one can go 10,000, and molecular mechanics like biology, where there is atom-atom simulation, you can go to 100,000 atoms. This is typically because of the scaling criteria, that if you look at the largeness of the system, let's call it capital N, then ab initio methods CPU time scales as n to the 4, and that is the cheapest like DFT, Hartree-Fock, but it can go up to easily up to n to the 7 today. And I hope you can imagine how dangerous from 4 to 7, because you have n cube, and if n is even 100, it is 10 to the power 6 times more, 10 to the power 6 times more computing CPU. So that's really large, and I always joke that if in a setup your Hartree-Fock problem is over in minutes, or by the time you take a cup of tea, the same problem for if you do an MP2, it might take a French dinner, which is typically 3 hours. And if you do couple cluster singles and doubles, you may take a full day. And if you do a CCSDT, you may have a vacation in Kerala and come back and see the results. So just to show, this is just to highlight how quickly it explodes, the time explodes from Hartree-Fock to MP2 to CCSD to CCSDT, and I will come to those methods later, but many of you already know those methods. So you must use a right method for your computer and your job, and that is what is called horses for the courses approach, and that is what I showed, multi-scale simulation. You must use in the horse racing, you have to put the right horse for the course, so it doesn't work otherwise. The people who know what kind of horse course is there, they know how to bet. So you have to put horses for the courses approach, and that is what the computational chemists are doing. Yet, if you say that I only want to apply biological system or very large system, why should I learn ab initio? That's a question that you can ask yourselves, but I will try to show that it is very important that you learn ab initio methods and DFT, and that is the spirit of this, this specific workshop. I think this has been already told before, 1926, 1927 has been alluded to in the morning lectures, I think Manoj said, but I want to re-emphasize that this is 100 years of quantum mechanics, and this is really a game-changing science. As all of you know, it has brought in new paradigm, it has a disruptive thought. The main disruptive thought is what I have written here, that probabilistic description instead of classical certainty. And actually, somebody said that if people are not surprised by this, then probably one has not understood quantum mechanics. So this is a very, very strong bullet that I don't have electrons, I don't know where the electron is, and that is the reason Bohr's model is eventually not correct conceptually, and of course it could not be applied, though it gave right results for hydrogen atom, because Bohr said that it moves in an orbit, which means I can track the electron. That cannot be true. Whereas when I do orbital description, there is a density, and density is basically smeared. So this is the main difference. And a very fundamental question which I would ask, which some of you should be able to answer, that this object or a cricket ball is made of electrons. But the electrons do not have certainty of position, but the cricket ball has a certainty of position. This also has a certainty of position. I know XYZ coordinate. So how does that happen? So how does it happen that when you go from atoms and small particles to a large particle, there is a certainty of position, there is a certainty, whereas for very small system, it breaks down. And this was actually very nicely explained by Niels Bohr himself in the Bohr's correspondence principle. He said that the limit h tending to 0, quantum principles move over to classical principles. Many of you have studied this in the BSc MSc, and that essentially meant that h doesn't become 0. H is a universal constant. So what did Bohr mean by saying limit h tending to 0? In fact, there's a lot of discussion on that. It only meant that the system size is so big that the h can practically be treated as 0. And in all such cases, I would now argue in a different way, maybe here also there is an uncertainty of position and momentum, but it is so small in terms of the size that we can never experimentally verify. There's a second line of interpretation, is that when you have an Avogadro number, such a large number of electrons, molecules come together, they interact with each other, those interactions reduce the uncertainty. So there are lots of interpretation. In fact, whole of the physics was very much agog with this thought that how does the quantum uncertainty vanish slowly as the size becomes larger and larger, and then the question is, what is large and what is small? I think this is a very important question. Many people draw a line of nanomaterials, and today nanomaterials are very important at that border. But more interestingly is that quantum mechanics was apparently a figment of imagination at the time it started, a theory which even Einstein did not think that it is right. But today it is generating quantum technology. Lot of you are already working on quantum computing, quantum materials, two-dimensional materials which are showing very nice quantum effects. So I think the quantum mechanics has generated technology. So there is no reason to believe that fundamental science cannot go to technology. And I think you know in ANRF, DST, DBT, everybody has a program today. Every science body has a program on quantum technology, quantum materials, and so on. I hope all of you have seen that, and I'm sure you people would be part of this as it goes. But my further provocative question is that could quantum mechanics be discovered by a computer system from pre-existing rules? Existing rules means not today's, at the time. When quantum mechanics was discovered, could artificial intelligence have discovered quantum mechanics? My answer is no, because it was completely disruptive invention. So it really came in a completely different way. The question of position, the question of psi and all that you already know, particle in a box and so on. The word quantum is of course very interesting. It is basically, without reading all this, I must say that this is basically lowest coin of money in some sense. When you give something, you have to give in terms of the lowest coin of money, and that is quantum. So that's your IGNOU, is what Max Planck said. So our lowest quantum of money is no longer 1 rupee or 10 paisa. When I was young, it was 1 paisa. Today it is, I don't know, 10 rupees maybe, the lowest kind of money. That means frequency is increasing. As the time, we have progressed, the time IGNOU has increased. So that is the lowest kind of money from where the quantum word actually came. And Werner Heisenberg actually wrote a very interesting letter to Wolfgang Paulin, where he described for the first time, and I think this has been also described today in 1927, the uncertainty principle. Though it already came, this letter was written much later. And there was a lot of interesting debate on quantum mechanics in the Solvay conferences. One of them was the 5th conference in Brussels, where this newly formulated quantum mechanics was discussed, and Albert Einstein was dead against quantum mechanics. Many of you know, I think this is a very interesting story, that Einstein did not like what apparently his own experiment started. That's a photoelectric effect. And ironically, Einstein got actually a Nobel Prize for photoelectric effect, and then he regretted that the mechanics that it has started, I don't agree. But Einstein could not prove it wrong. Heisenberg and Schrödinger eventually prevailed, and it was also a very interesting part of the history. Those who are interested may actually go. The Copenhagen interpretation is a metaphysics, which again I will not go into it, but those who are interested in metaphysics, in fact in IIT Kanpur, I don't know Manoj now, IIT Kanpur, we were participating as a student on metaphysics class in the evening with A.P. Sukla and possibly one more quantum mechanics person at that time. So it's very interesting debate. 6 o'clock, those who are interested would have come for just a free discussion on metaphysics, philosophy of physics. So I think it's very important to learn that quantum mechanics has generated a lot of interesting metaphysical pictures. There's a very nice book, those who are interested to read, Hans Henning von Gruenberg and Alex Griffiths, lovely journey through the early days of quantum theory. Let yourself be fascinated by the struggle of the great minds of physics in the birth of quantum mechanics. So it has not been a very easy journey, because a lot of people have discussed, a lot of fights, and eventually, of course, the quantum mechanics has come.
Since you mentioned,
Yes.
so I'm organizing these days a set of lectures, talks on physics and philosophy. So we recently finished Einstein's paper on photoelectric.
Great. Yeah.
What it means. Right now we are doing EPR.
Oh, fantastic. Fantastic, yeah. Because, EPR paradox and the Bell's inequality, they all came at the same time in 1930s and early 40s. So those who are interested should read. There is a fantastic
Quantum computing.
quantum, yeah, right. That is where the quantum entanglement comes in. So a very interesting thing. I was reading a very interesting book. If anybody, it's in the I think in the internet, so you can free downloadable. Putting the U in Quantum by Jack Savitsky. Please read this book. There is a nice quotation by Heisenberg. What we observe is not nature itself, but nature exposed to our method of questioning. That's very important. So we don't know what the nature is. Like spectroscopy is a method of questioning, and you see something, right? So, but does the nature does not exist? Is the nature not real? It is real, but it is not the same that we see. And there are very interesting debates here. In fact, there was a debate in the ISF, India Science Festival, on 10 January 2026. The topic of the debate was the world is an illusion, a quantum perspective. But of course, this Maya is not real Maya. It just says in the Heisenberg's term that it is not what we see. And Heisenberg actually did a very interesting, not Heisenberg, this Jack Savitsky actually did a very historical quote. I think it was Wigner and his students, his Jimenez, they were doing an experiment of some atoms in field. So the experiment was in the chamber. Jimenez already did the experiment and found out which state the system is. Because this is a wave-particle duality. Wave is essentially a combination of superposition of state. As soon as you make a measurement, however, the wave puts to a particle. So they already knows what is the state, and her boss Wigner is seeing it from outside. So he does not know which state the system is. He only knows it's a superposed state, whereas Jimenez, standing there, knows already what the state is. what is real? The question that Jimenez asked, what you saw is the real or what I saw is the reality? I think these are very interesting topics, and these are quoted on a very historical anecdotes, no equation, nothing, like they are sitting on a seesaw and discussing the quantum mechanics. So please good, and the book is downloadable, completely downloadable, free, putting the U in the quantum. I started reading this book merely because of this, that the debate that I told you, I was the one who was speaking for the proposal, that the world is an illusion, a quantum perspective. This was a public debate in India Science Festival on 10th of January 2026. So I was on the debate, and Professor Arun Pati, many of you may know, he is a physicist from Harish Chandra Research Institute, retired, and now joined KIIT Bhubaneswar and looking at the Center for Quantum. It was very interesting that he decided to speak against this, that the quantum mechanics perspective is not an illusion. And then 5 days before the debate, he calls me, he tells, can we switch our positions? I said, that's not fair. Everything flyer has gone that you are speaking against it. Then he almost started converting this into a panel discussion, because he said, no, more I am thinking, this is right, I think. The quantum perspective, the world is an illusion. I told that I was anyway surprised, because you are looking at the Center for Quantum and you decided to speak against it. So I was actually surprised. I told Arun that I don't know, but I said now the changing look will look very bad, because flyers have gone just few days before when I was preparing. So I think there's a lot of interesting thing about the superposition wave versus particle, what you see, and that is the Copenhagen interpretation. What is that? Once you make a measurement, the Dirac makes a very interesting statement. I don't know if you have read Dirac's book. Dirac's quantum mechanics book you must read. Dirac says every measurement is immediately repeatable. Actually, people didn't understand what Dirac meant. It meant that when you make a measurement for a superposed state, everybody will may get different results with some probability, right? And those are basically the eigenstates of that measuring operator. I hope all of you know this, if it is a superposed state. But as soon as you make immediately the next measurement, it will be repeatable, because these systems have now gone from identical system to different eigenstates by the first measurement. And the second measurement, now it's an eigenstate. So it's a stationary state, so they will continue to get the same value. Actually, this required a huge debate, and people, up today we understand, but those days people said, what do you mean by, first of all you say, you don't know what values you will get. There's a now you say second measurement is immediately repeatable. So I think it was a huge, interesting debate. And that Dirac's book also, I must say, that very few equations are there. Many people said that it's a good bedtime book. I'm sure it's a good book to fall asleep, at least. If you are not feeling asleep, read that book. All right, so I already talked about small to large, and I even make a provocative statement, is classical mechanics an approximation of quantum mechanics? Because quantum mechanics should be the truth. Because everything is composed of atoms and molecules. Because of large number of atoms and molecules, certain approximations are taking place, which looks like a completely classical. So, but unfortunately, I can't ask this question to you, because you have first studied classical mechanics and then you studied quantum mechanics. And all of us have done that. So it is very hard for us to accept this. But I ask this question, that I believe classical mechanics is an approximation of quantum mechanics. When the scale becomes very large, the approximation leads to classical mechanics. Yes?
So how immediate is immediate in the case of measurement?
Yes, so now the delta T is 0. Okay, delta T is 0. Yeah. To be honest, so it means that the system should not evolve in time.
That was direct delta function.
Yeah, so I think, I think this is a difficult question. At this point, philosophically, we will say that system has not evolved. It has just remained there. But you are right. It's an interesting question. What is immediacy? All right, so I will skip some of these slides here, because they are not interesting. But I must quote these 2 slides. I have kept a lot of things here which I will not show. 2 quotes. One is by Quetelet in 1828, 200 years back. Read it. The more progress physical sciences make, you will be happy actually. The more they tend to enter the domain of mathematics, which is the kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. Fantastic. I mean, all of you are in the good books. But look at the next sentence. By Comte in 1830, all synthetic chemists will be very happy. Every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, then he says it's an aberration which is happily almost impossible. It would occasion a rapid and widespread degeneration of that science. So you can see within 2 years, these two quotes are completely contradictory. Of course, we know that the second one is now wrong. It hasn't degenerated chemistry. In fact, it has strengthened chemistry. That is something that I want to must tell you. But somebody might tell you this. So then you go back to this. That's very important. And this is done within 2 years of 1828 and 1830. All right, I think this is something which has been already talked. Why 2026 is because this paper actually came. Many people recognize this is the first paper in quantum mechanics. These are debatable. But interestingly, there is no word quantum here. If you look at it, it's a German thing. It has been translated. It just says an undulatory theory of the mechanics of atoms and molecules by Erwin Schrödinger. And this paper actually lays down the postulates of quantum mechanics. And that is why 2026 is a year of quantum mechanics, 100 years of quantum mechanics. But then chemists are interested in molecules, and we have again discussed this. 1927, as I think Kalidas and Manoj and all said, that the chemists are smart. Within 1 year, they came up with the description of hydrogen molecule, the Born-Oppenheimer approximation. A lot of interesting things came up with Oppenheimer's paper within 1 year. And of course, the start of the valence bond theory. At that point, G.N. Lewis, who was actually doing valence bond theory, according to me, left the field because he didn't like quantum mechanics. G.N. Lewis was looking at all the bonds and octet rule and so on. And Linus Pauling came, and many people thought that had G.N. Lewis been alive, he would have probably shared the Nobel Prize with Linus Pauling, but I'm not very sure about it. The Linus Pauling and many others actually looked at the valence bond theory. Pauling eventually, of course, got the Nobel Prize, as all of you know. But this was a very interesting work by Heitler in London. I also want to announce that the international, maybe some of you are coming, International Society for Theoretical Chemical Physics is organizing a conference in Argentina in next year, in I think August 2027, on the 100 years of quantum chemistry. And that will be a very interesting conference. I think Gustavo Auker is organizing this in a little bit north of Buenos Aires. So that will be a fascinating conference. A lot of people are coming. It will be actually 100 years of quantum chemistry. Those who are interested in the early development must read. I mean, I used to read Pauling and Wilson, very, very famous book. I don't know how many of you read these days. Linus Pauling, E. Bright Wilson's 1935 book, Eyring Walter Kimball's 1944, Heitler's 1945 book, Elementary Wave Mechanics with Applications to Quantum Chemistry, and of course Coulson's 1952 textbook, Valence. I think there are so many books, but I could just give you a few of them which are of great interest, I think. Very quickly, I think a lot of people have talked of history, but I should start after 27, 28. Heitler has published the quantum mechanical calculation of helium. In fact, today the helium was discussed, and completely numerically, Heitler has actually solved the problem. Numerical solutions are not easy, but it was possible for atoms. For molecules, it is very, very difficult. 1930 is when, today we talked of Hartree-Fock, and I'm going to go back to the board or somewhere to show the Hartree-Fock a little bit, because already Hartree-Fock has been covered. But the first publication of the Hartree-Fock equations, and this is the beginning of what I call molecular orbital theory. And very quickly you will see valence bond got outdated. MO theory became the in thing, because valence bond had a lot of problem of orthogonality of the orbitals, so they had to abandon molecular orbitals by constructions were orthogonal, or orthonormal, to be more precise. 1933, James and Coolidge published quantum mechanical calculation on hydrogen atom, very early molecular orbital theory. This is a very good paper. And the modern quantum mechanics started. People started looking at the solution of H psi equal to E psi. So that's the time independent equation. And already you know from the morning lecture, so I'm not going into that, that as soon as you are interacting particles in the electrons in the Hamiltonian, they are not exactly solvable. And that is why the problem is there. My friend used to always joke that you all quantum chemists have only one equation, that also you could not solve. So many years. Many of you know that friend, so I'm not going to tell his name right now. I mean, it's true in some sense. Because this equation could not be solved, it has actually created a generation of chemists and quantum chemists. Okay? And you will see, I mean, how difficult this equation is. Particularly larger and larger system, people are still looking at strongly correlated system, lots of interesting work. But I think I just want to tell this is the equation that we are interested from 1920s. Okay? And this is the Copenhagen interpretation that you measure, you get from density to a particle state. I will not go into this. So this is basically the problem. The problem, as Professor Manoj Harbola was telling, was that when you come to helium atom, this is the problem. Because this 1 by R12 cannot be separated as a function of R1 and R2. You cannot write 1 by R12 as any f of R1 plus f of R2. If we could do that, the entire problem would have vanished. Because this would have become again a non-interacting problem. Up to here it's non-interacting. But this cannot be done. That's mathematicians have actually tried this. I must tell you that can we not try as accurately as possible, and that will actually lead you to Hartree-Fock later. Eventually that is going to lead you to the Hartree-Fock. So this is the problem why we need quantum mechanics. Yes. Yes.
And I think morning I should have made that. You have this 1 over R12 term, but the confining potential is harmonic, then it can be solved exactly.
That's true.
So harmonium. So
Yeah.
everyone should know that's a
That's true. That's true. But not all states. But yeah, right. That's true. Yeah. So of course this is not such a case. You know that. So, all right. So then we of course have a lot of problem how to make approximations, how do you take this repulsion term, and so on. Of course, you have variation method. Then, first of all, for the molecule, we do Born-Oppenheimer approximation to simplify. Then, for the electronic problem, we use variation method. That led to Hartree-Fock and DFT, etc. Already, you know that the second Weinberg-Kohn theorem is basically based on the variation method. And in fact, first Weinberg-Kohn theorem is also proved by variation method. So variation method has been a very, very important method. So I always tell my students to, after first introduction, read variation method as a mathematics. And variation method is a lot, and perturbation theory, of course. These two things are very important. And there are theories which are called VPA, variation perturbation theories. In fact, you can do variation within variation, perturbative equation, you can solve variation like MP2 equation. Write the MP2 equation, but don't solve it by basis sets and the way it is done. Solve it variationally. What kind of functional will give an upper bound to the second order MP2 energy? Lot of interesting things have happened. So those who are again interested, I must tell you one book called S.T. Epstein, Variation Method in Quantum Mechanics. This is a very good book, Saul T. Epstein, E-P-S-T-E-I-N. And so this is a very good book in which they discuss a lot of things. Variation within perturbation. Once again, the proof there has been described in first few chapters. Yes.
Don't quote Epstein. Other connotation these days.
I'm sorry about that. Epstein has other connotations. So I'm sorry about that. I'm talking of Saul T. Epstein, so I wanted to make sure. Yeah, I agree. So I think that's a very interesting book because I read a lot of this. I could not still complete the entire book because there are a lot of things, a lot of nice appendices. There are upper bound. Many people talk of upper bound. Do you know there are lower bounds? Lower bounds are very, very important because, Eckart's lower bound. Because if you have an upper bound and a lower bound, then it is very beautiful. You can keep on refining both of them. Your energy is right in between. It can't go above, it can't go below. So there have been lots of interesting things. Parallel Lovedean is one person who likes to play with this. So read Lovedean's papers. There's a separate lectures. I can give only on what Lovedean has done. Very interesting person. So he used to play around with this. Many of Lovedean's work were finally not implemented because it's very hard. But his ideas were very interesting. I used to love talking to him on a poolside dinner. He was an exciting person, actually. He never used to like computation, incidentally. So he used to dislike people who are using Gaussian, even in that 1990s when I used to meet him. So this is the Born-Oppenheimer approximation, where you first separate nuclear and electronic motion. So what we are going to talk is only the electronic Hamiltonian. And I have written down the electronic Hamiltonian for n number of electrons, small n number of electrons in capital N nuclei. So as you can see, these are the alpha goes with the capital N and small I, J goes over small n, and that is essentially the electronic Hamiltonian. So we have removed the nucleus kinetic energy and nuclear repulsion completely. This works because the mass of the nuclei is much larger than the mass of the electron, and we can consider the electronic motion in a field of fixed nuclei. So that is something that is probably the best, easiest way to understand Born-Oppenheimer. What it is done is written here. But though the actual approximation is much more complex, and you have to find out at which order this works. So already in the morning we discussed this, that if you have a trial wave function, this is always greater than or equal to E naught. So basically we minimize through some parameter, lambda, whatever is a lambda parameter, you minimize the energy, then you get the wave function as accurately as possible. Simplest approximation, since this has been discussed, but let me set things in motion. The many-body electronic motion as a determinant of spin orbitals. Determinant is simply because you require the wave function to be antisymmetric. I am using chi for the spin orbital symbols. So this is a determinant. As you can see, if you interchange any two coordinates or any two spin orbital, the psi will become negative. I think all of you know this. And this is, of course, a 1 by square root n factorial is merely to normalize this. Then comes the Hartree-Fock. We want this such that the energy should be now minimum. Now we apply the variation method. Why do you do the Hartree-Fock? Because the chemists want a simple description. What is the description? That I need a wave function of n electrons and n spin orbitals. So that is what I need. I have n electrons, capital N electron. I need to define n spin orbital. So I can easily say which electron is in which, not which electron, but I can say there are n electrons in n spin orbital. You decide which electron is where. I don't care. But that's the simplest approximation, and that is why chemists love single determinant. Chemists do not love anything that go beyond. Interestingly, why has DFT become very popular? This is my theme. Is that DFT does not have a wave function per se, but DFT has a quantum determinant from which the density is coming, which chemists like, for the reason I explained. Because you have n spin orbitals and n electrons. As soon as I go beyond this for ab initio theory, you will start disliking it because you will start asking me questions. Where is the other determinants coming? Are they excited states? A lot of questions will come, but they are basically included in the ground state. But this is the simplest way. The question is which set of spin orbitals is best. So that is where I use variation method, and you get the Hartree-Fock equation. So that's your Hartree-Fock equation. I have quickly done in this slide so that I avoid time, this time constraint. But this is basically the spin orbitals, and this is the extra potential that you come from the kinetic and one electron attraction. This is, of course, one electron potential. This is the effective potential. Now you can see this effective potential is an average of 1 by R12 between chi j star and chi j. This is what was first shown in the first morning by Professor Harbola, that this part can be easily written with the density. You will see that very easily. The energy from this part can be written in terms of density, but then there is a sticky point here, P12. What is P12? It's a permutation operator. So whenever it acts on something, the 2 will become 1, 1 will become 2. That's the permutation operator, and as soon as 2 becomes 1 here, then there is no density. Chi j star 2, chi j 2 has a sense of density. As you know, if you sum over all j, it will actually become a density, as again has been told from the Kohn-Sham determinant how to get density. But this guy creates the problem, and that is the exchange. And unfortunately, as you can quickly see, this exchange I cannot write by exactly with the density. And that is where I am comparing the DFT. This is where my agony with DFT starts. The first agony, I can't write the exchange energy. Whereas in the Hartree Fock, I have exact form of an exchange energy. I am using the spin orbitals explicitly in writing this Fock operator and eventually also the energy. Okay? So this is the Hartree Fock, Coulomb part and minus the exchange part, which is both stuck in here. The same thing, and this becomes my one particle equation. Solve this just like you will solve any one particle equation, get the chi's, bring in your determinant, and eventually you will get the energy also. Energy is quite easy to get after that. And that energy, except for the exchange part, can actually be written with the density. So it's not a problem. You can actually write, but this is the part that you cannot write. And of course, there is something more that I am going to tell, that this Hartree Fock itself is not exact in ab initio theory. That will be called correlation. And those are the two parts which they have been discussing. Plus a third part which will come is the kinetic energy part, which will come a little bit later. What is the problem of DFT in kinetic energy, which is not a problem in ab initio theory. None of this is a problem in ab initio theory. So that is the reason we said TS, V exchange, V correlation, which have to be empirically or whatever, which has to be somehow formed. All right, but the important thing here is that this is a self-consistent field, which is also the same thing for DFT Kohn-Sham method, because you have a Fock operator whose eigenvectors are the spin orbitals, but the definition of the Fock operator already includes the spin orbitals. So you have to do it by a self-consistent field, but this is same as Kohn-Sham equation. You have to do by self-consistent field, except that the form of the operator will be different. So I'm of course using orbitals. I hope all of you know what is an orbital. Orbital is simply a one electron function. Please remember, don't write orbital is there where the density is maximum and all that. Orbital is simply a one electron function. So it could be a Hartree Fock orbital, it could be a Slater orbital, it could be a Gaussian orbital, it could be anything. Everywhere you use an orbital because that's a one electron function. So you start with the initial orbitals, compute the average potential, essentially the Fock operator, solve for the new orbitals using this new potential and keep repeating. That's basic thing. Of course, there are a lot of details because the solution is not easy, particularly for the molecules. You have to bring in lots of basis sets and all that. And this will become a matrix equation. So a very simple thing, a spin integrated Hartree Fock for closed cell system. Let's say water molecule, you have 10 electrons, and you finally get these orbitals, special orbitals, which is now has the same Hartree Fock equation. Please remember, I was using chi for the spin orbitals. Now I have switched to phi. These are my special orbitals. You have a simple equation for the closed shell. It can be done even for open shell, but closed shell it is very simple. You have the same Fock operator, except that in the Coulomb part you have a factor 2. That is very, very important. Whereas the exchange part, there is no other extra factor comes. Otherwise, the Fock operator is exactly identical. Now, physically, why does the Coulomb part have a factor 2? Because when I am doing an averaging, for all of these, I can have a Coulomb repulsion. Let's take an upspin. Let's say this is an upspin orbital, space orbital with an upspin. This upspin can have a Coulomb potential. I had already told you there is a Coulomb potential is this first part and the second part is the exchange. Coulomb potential with either this or this, because in Coulomb potential, these two orbitals here were both chi. So it doesn't matter. If this is beta, this will be also beta. There is no orthogonality. So the alpha spin will have an effect from the upspin and the downspin, all of them. So that's why there is a factor 2. But in the exchange part, yeah, this has unfortunately gone away, so this should be here. Anyway, the exchange part, if this is an alpha spin, it will have no effect from the beta spin because alpha and beta will come here and they will become integrated, they will become 0. So the exchange of the parallel exchange takes place only among the parallel spins. Just remember this. Whereas Coulomb repulsion takes place among all pairs of spin. So then you will understand why in the exchange there is a -1, whereas in the Coulomb there is a +2. And in fact, just give this, you can easily write down in terms of Coulomb and exchange the energies, total energies. Very, very easy. If I tell you J and K are the values, you don't have to know what is the value, you should be able to write this. So for example, if I have just this, let's say I have only 2 electron molecule, H2, then this will become small h of 1 plus small h of 2, and there is only a Coulomb repulsion. There is no exchange here, J12, J11, because both of them are in 1, J11. If it is between 1 and 2, it will be J12, like let's say 4 electron molecule, then it will become h of 1 plus h of 2 plus h of 3 plus h of 4, and then there will be a J11, there will be a J22, there will be a J12, there will be a J12 twice, because there are 2 pairs of electrons, and there are 2 times K12, because you can see between these 2 electrons, up we will have an exchange with this up, down we will have an exchange with down. So I can straight away write, for example, what is the chalk? Yeah. I can straight away write for a 4 electron, which is phi 1 square, phi 2 square determinant. I can straight away write it is h of 1 plus h of 2. I hope you understand what is h, small h, it's just the kinetic and the 1 electron attraction. Then about J and K, I can write these two J11 plus J22 plus 2J12, because I have this, and then minus 2K12. So I'll have 1 with 2, 2 with 1. So you can see eventually there are 4 pairs, 4 electrons, there are 4 pairs of interaction. What is 4C2? 6. So that is what has actually come. And you can actually write those things very easily. If you understand this, you can actually write just by inspection. You don't have to solve the Slater rules and all that. Just by inspection, one can write these values very, very easily. So how many pairs of interaction between 1 and 2 are there? How many pairs of interaction between of the first spin, up spin, how many pairs are for the down spin? So you should be able to write this. This is a very first thing that we always do when you teach Hartree-Fock. However, when you do Hartree-Fock for molecules, things are more complicated, because I can't use a numerical solution of the Hartree-Fock equation itself. So what is done is actually introduction of a basis, and this is the same thing for the Kohn-Sham. The DFT has a complete similarity. Till this time, only the operator is different. Otherwise, if you just forget about the operator has exchange correlation, all that you learned, but otherwise everything is same. So you do the same thing. So what you do, this is what Ruthan first did. It's called Hartree-Fock-Ruthan equation. You put this phi as a sum over C mu I phi mu. These phis are the atomic orbitals that I'm now using. Another notation. So I put this here. Then I integrate by phi nu star. I multiply by phi nu star and integrate, and both left and right hand side, and call this a matrix of Fock operator between 1 phi mu, 1 phi nu. That's a basis set. You get this simple matrix Hartree-Fock-Ruthan equation. So this is very simple. I think all of you can see this. If there is any doubt, please ask question. It's very easy to derive this. Okay. So basically, you multiply and integrate. Multiply each phi nu. So eventually, you have n number of equations. If there are m number of basis set, there are m number of equations. So everything matches, and you get a matrix equation. This equation is very often written like this. As you can see, if I define Fock matrix, if I define overlap matrix, you can write there like this. This, however, is not a simple eigenvalue equation. As you can see, what would have made it eigenvalue equation? Anybody can say? If I wanted this to be an eigenvalue equation, what would I wanted? S to be unit matrix, right? If S were unit matrix, then it would have been an eigenvalue equation. However, S is not a unit matrix, unfortunately, because it's an overlap matrix between the atomic orbitals here. And those atomic orbitals, please, a lot of people have this problem. Those atomic orbitals are based on different atom center, like methane. You have a carbon atoms, 4 hydrogen atoms. So atomic orbitals on one atom are orthonormal. But when you mix them up, they are not, because they have different Hamiltonian. Carbon has a different Hamiltonian from this hydrogen. This hydrogen also has a different Hamiltonian from this hydrogen, because now they have specific coordinates, relative coordinates. So they cannot be orthonormal, and that is the part of the problem, that this is not such an easy equation. This has to be still solved by self-consistent field, because in the Fock matrix I have this Fock operator, which again I don't know. So you have now a self-consistent field equation and yet a non-eigenvalue equation here, matrix equation. So what is done, and this is a part that is very little, many people don't understand this part. What is done in Hartree Fock is the first thing is to orthogonalize the orbitals. You start with the atomic orbitals, then work with what are called orthogonalized orbitals. There are many ways to orthogonalize. In fact, the most standard orthogonalization that is used is the Lovedean orthogonalization. Many people, that's a symmetric orthogonalization. You can use canonical orthogonalization. So there basically you have to transform the orbitals by inverse square root of this S operator. And then you get, so basically you transform these phi's to some orthogonal set, phi prime, by an operator transformation x, where x is nothing but s to the minus half. And one can show that this will orthogonalize. So that is what Lovedean's, this is Lovedean's orthogonalization. Canonical orthogonalization is diagonalize the s and use u s to the minus half. Anyway, these are all small variations. But basic idea is that I have to first orthogonalize. So when I do Hartree Fock, remember the first job, every Hartree Fock code, I don't know if you have ever written, because we have written Hartree Fock code in hand. I have written in hand when CDAC first came, I parallelized also, 1989, 1990. The first job that we do is after evaluating this S matrix, that calculation has to be done, is to diagonalize the S matrix. Because I need S to the minus half. I don't know if you know how to calculate S to the minus half. It is not an easy thing. It is a square root of a matrix. Even any a to the power half, doesn't matter. So how do? You first diagonalize this. So you diagonalize S. So you form U dagger SU as a diagonal SD. Then you form SD to the power minus half and then back diagonalize, back transform, and that will give you S to the minus half. You can see this very quickly. It's very easy to do. You can actually do for any function of S, and I can show this. For example, if you have a function of A, operator A, Hermitian, but the operator has to be Hermitian. That's the only thing. So I can write this as a Cn a to the power n. So I'm going to construct a to the power n, but first diagonalize A by the same way. So I have a unitary transformation, U dagger AU equal to AD. Then I write U dagger A to the power n, U. If you write this, you will see that a to the power n can be written as e to the power a, etc., u, and bring between the pair of a's u dagger, because u dagger is identity, right? It's unitary. Then you will see there are n times u dagger au, n times. Each u dagger au is already ad. So you get ad to the power n, which is very easy to form. Diagonal to the power n is very easy to form because just make them diagonal. Any function of diagonal matrix is easy. And then you now know u dagger a to the power n, u is ad to the power n. So a to the power n is just reverse transformation. U ad to the power n, u dagger. Right? I hope you understand this. It's very easy because you have u dagger is identity. So you can actually do this very, very easily. And that is what is done. If I can do for a to the n, I can do for any function of a. Because I do the same thing for each of them, and that whole thing becomes function of ad. So in that case, what will happen is that a function of a will be u, function of ad, u dagger. I hope you understand. Yes. Huh? Oh, sorry. That was in a hurry. Yeah. So it's just a power series expansion. Yeah. Function of a can be like function of number can be written as x to the power. Yes.
With quite a lot.
Yeah.
If you could comment for this.
Yeah.
If the number of basis sets is more than the number of electrons, then you get more orbitals than the number of
Yes.
electrons. And what,
Yes.
can you
Yes.
just comment on that?
Yes. I'll come to that. That's important. Yeah. That's very important. You have to have more. Otherwise, if you have just that, then the Hartree Fock quality is also bad. And later on, I can't do electron correlation anyway. So that will become the bigger problem for me. Yeah. So I hope you understand that even this small part requires a lot of understanding. This small part requires a lot of understanding how to do it. So the first part of the SCF code is actually to diagonalize S and then form this S to the power half, and then you can keep doing it. So each time you construct the Fock matrix, each time you construct this Fock matrix in that orthogonal basis. So there is a way to go, X dagger Fx. So same X can be used, and then do the complete solution, and depending on the basis you will get the number of orbitals. So anyway, this is something that I have written it. So this is what we are doing in the mu. All right. So now what are the atomic orbitals? That is a very, very important question. Atomic orbitals should be typically Slater type orbitals. Okay? They are better behaved than the Gaussian. But the problem is that the 2 electron integrals are very, very hard. You will see when I calculate the energy and so on, I will require in the basis set integrals which are called 2 electron. Again, it is the same thing in DFT, incidentally. These are all common thing in DFT. So I will require an integral of this kind, phi mu star 1, phi nu star 1, 2, 1 over R12, phi lambda star 1, phi delta 2, delta 1, delta 2. So these are very typical integrals which take the hardest time. These are called 2 electron integrals. I can have a simple notation to write this as a mu nu lambda sigma. This is called the Dirac notation. Many people write this in Mulliken notation. It doesn't matter, where you bring in this 1 here and then 2 there. So remember, in the Dirac notation, the left is complex conjugate, the right is not. That's the only difference. But you have a 1, 2, 1, 2. In Mulliken, it will become 1, 1, 2, 2. Just by interchanging 2 and 3, you can get to Mulliken. That's not important. The point is that these integrals are typically based on 4 centers, because you can look at these 4 atomic orbitals. In a polyatomic molecule, I told you each of them can be different atoms. Like even in methane, one can be on this carbon, this hydrogen, this hydrogen, this hydrogen. So you have already, so typically tough integrals are 4 center, 2 electron integrals. And these are the hard things to evaluate. So most of the SCF time in the beginning goes in evaluation. This is of course one-time job, but it is a very, very important job, and they are very hard to calculate. But once you have them, they are better behaved than Gaussian. But unfortunately, all of us use Gaussian. The Gaussian integrals are of this kind. The functions are of this kind. The 2 electron integrals become simpler, but you have a wrong behavior at the nucleus and decrease too fast with the R. So what happens is the following. This integral is hard to calculate. But as soon as these become Gaussian integrals or combination of Gaussian, because Slater cannot become Gaussian. So what do? We make them as a combination of Gaussian. Then Gaussian has a very, very important thing, that if you have a Gaussian between GS star and GB1, then this becomes another Gaussian somewhere between A, B with a function 1. So product of 2 Gaussian is a Gaussian where only the center changes. Where does the center come? I have not written the center here. But remember, wherever I am writing R, it is R minus the center of capital R, where the atomic center is there. So each R is like that. If you interpret that, the Gaussian becomes eventually a 2. So all this becomes only one 2 center and another center. So it becomes 2 center integral, all of them. So there is no 4 center integral. And that makes it very, very easy. So this is again a mathematics. Those who are interested in the Gaussian integrals, how to evaluate, should go to Journal of Mathematical Physics, 1960s. Fantastic papers are there where all these integrals are actually solved. This is basically mathematics. So that is the reason we use Gaussian, even though each of the Gaussian is not good. So what do? You write one Slater orbital as a combination of Gaussian. So you know in the basis set there are 2 things. One is number of Slater orbitals, then the expansion of each Slater orbitals in terms of Gaussian. What Professor Harbola was asking was the number of Slater orbital itself is much more than the number of electrons. So how they are expanded is unimportant here. So I am going to come to that. When that happens, what do we do? They are called the virtual orbitals. So what I will do with that. But the important part is that I have these orbitals. So typical Popel's base is because I asked this question to a lot of students and they are not very sure what they are doing. So for example, if I have a 631G, let's just look at a very simple basis. It means this purple basis says this separator is just for, this is only a symbol, notation. And you can have your own notation. But the separator means this is one core orbital. So let's say I took a carbon, just as an example. So I have a carbon 1s, Slater orbital first. First I'm talking of Slater orbital. This is valence. What is valence in carbon? 2s and 2p. So I have two entries, not 3 and 1. Don't look at 3 and 1. Just look at the number of entries. So I have 2s and 2p twice. So I have 2s prime, I call it 2p prime. So for this carbon atom, I have just got these many Slater orbitals. Just these many Slater orbitals. If I do a calculation of methane, I can do the same thing for hydrogen. You will clearly see what he was telling is that you will get still the number of orbitals which are much more than the number of electrons, even in the modest basis set. I will come to that. But I don't work with this. I work with Gaussian. So what does this mean? Now it says that this 1s orbital is expanded in terms of 6 Gaussian. These 2s and 2p is one set which is expanded in terms of 3 Gaussian. And this is another set which is expanded in terms of 1 Gaussian. So that is what 631G means. Number of 631 is basically number of Gaussian that is required for expansion. That does not increase the number of Slater, it does not increase the dimension of the problem. So number of molecular orbitals that you will get with that question I will answer will depend only on the number of Slater. It doesn't matter what are these. But what this will do is to refine the Slater orbitals better and better and make those integral evaluation easier. That's at the back end happening. What I am going to get is just the number of atomic orbitals which are Slater orbitals, and that is my Fock matrix. So I will get, if there is a capital M number of orbitals, I will clearly get capital M number of molecular orbitals. Okay? And clearly you can see they are very large. So if I take methane for example, in 631G basis, you can already see for carbon I have 1, how do you calculate? 1 plus 2 plus 3, 5 plus 4, 9. So I have got 9 bases for carbon, right? If I do for the hydrogen, hydrogen has no core. This is for core. So you have only valence or 2 valence. So carbon has 9 electrons, 9 orbitals. Hydrogen has 2 valence, I will call it 1s, 1s prime. One of them will be 3 Gaussians, another will be 1 Gaussian, but that's at the back end. Number is 2, so your total number is 9 plus 2 into 4, 8, 17. So I get 17 orbitals. For a methane calculation, so if you do this calculation, you will quickly see you have a 17 orbitals. For methane, okay, I am not calculating, here there is no d orbital, that will come as a polarization star and all that. It's a very simple thing. And you need how many orbitals for methane? 5. Because you have 10 electrons. These are special orbitals. So each of them can take 2 electrons, right? I need only 5. I have got 17. So that was the question. What happens with those 12 orbitals? Now those 12 orbitals are very important. First, why did these 17 orbitals come? Because my basis is better. More number, if I do 6311G, I will have even more orbitals. Then each MO is getting better. Okay? So I need more and more orbitals. So a basis set, the simple thing is more the merrier. A very simple thing, everything. Now each of them will also be expanded in terms of Gaussian. They are not contributing to the number, but if these numbers are also large, it is good. Then STOs are also better described. STOs are also better described. The second point is that these extra 12 orbitals will now become my virtual orbitals. You will later see when I expand my ab initio method, these virtual orbitals will be used for expansion of what is electron correlation. These virtual orbitals, even in Kohn-Sham, gives you what is called electron affinity. In a very simple way, the electron affinity is the negative of the LUMO. So they are basically unoccupied orbitals. The lowest of them are LUMO. And all of you know that LUMO has a very, very important role to play in all reactivity and so on. So of course virtual orbitals are important, but it is not the LUMO. If you have n plus 1 electron system, you can have a combination of all the unoccupied orbitals. So more the better. So that would be my answer. It's always better. And they are certainly used for certain properties like electron affinity and all that. So they are very, very important.
What about BSSC?
Huh?
BSSC.
BSS is a completely different thing. When I'm looking at binding of two systems, then the BSSC will come. I'm only looking at methane right now, but methane reacts with something else, then the BSSC will come, because what he is telling is that the super system will have more number of bases than each of the fragments. So there is an inconsistency that may lead to a kilojoule, whatever error. So to do that, what they do is to do a ghost atom. So A and B are reacting molecule. So when I am calculating for A, I am going to count the B basis set, though B is not there. That is why they are called ghost bases. When I am calculating for B, I will put the basis in A as in imaginary basis at the same point. So whenever I am calculating A and B or AB, total number of bases is always same. So that is how I avoid BSSC, but that is true only when there is an interaction energy. So in this case, you have just methane total energy, so I don't care. But better, bigger, the better. That is the most important thing. Bigger, the better, yes.
So can I do a calculation where I restrict myself with number of bases or STO bases equal to exactly the number of electrons?
Okay, so let's try that. So methane has 10 electrons. So your basis will be a special basis. So you have to have only 5 orbitals. So 5 orbital meaning you will have a big problem. Hydrogen minimum 1.
Is that your battery or your laptop's battery? Your battery doesn't have a
No, my laptop battery.
laptop battery. हमारा एनर्जी तो लो नहीं जाता.
हमारा बैटरी तो नहीं जाता है, इसको लगा दो ना, इसको लगा दो. अच्छा, so now you see the difficulty. You have to have minimum 1 hydrogen if you want to distribute. एक कार्बन 4 हाइड्रोजन में काम नहीं होगा. अच्छा, of course somebody can say, physicist will say, why do you need LCAO? I can take all 5 orbitals from carbon. Perfect. As far as, because one set of orbitals, one electron function is expanded in another one electron function. I don't care, but it will get bad results. So the physicist always asks me the question, why do you need? But then you will get a bad result. They will say, take all 5 orbitals from carbon.
Basically, your basis is bad.
That basis is bad. So chemistry will not even look at that basis. Minimum is STO3G, incidentally. The worst is STO3G, but even then, STO3G is the minimal basis. So carbon में you have got 1s, 2s, 2p. मतलब ये जो prime वाला है, वो हट जाएगा. Valence. And hydrogen also prime हट जाएगा. Hydrogen also you'll get 1s. Now if you calculate, this is already 5. 5 into 1, 1 into 4, you still have 9. So this is the lowest number of orbitals that you can have. You still have 4 virtual orbitals. And which is good. Because if I want to do for electron correlation, CI, couple cluster, I need virtual orbitals later. So I think it's important to have virtual orbitals. So yeah.
And these are in a way self-consistent virtual orbitals.
So they have been. Now here there is a question that if you do DFT, people say that the Kohn-Sham virtual orbitals are better than the Hartree-Fock virtual orbitals. You can have a, just see, where is the thing gone?
Wait, I will. It's okay.
No, not this. वही था. That one.
Which one?
No, that one, no. Perspective. Yeah. So the best thing about Kohn-Sham is that the virtual orbitals are very good. So if you have a virtual orbitals from Kohn-Sham and then people have done this, then do a CI. So this is real mixing of ab initio and DFT, and then they claim that the CI converges faster because Kohn-Sham virtual orbitals are very good. In fact, I wanted to mention that Kohn-Sham is really good actually in many ways. In some ways it is not good. I will come to that also when I do couple cluster, but it can be very good actually, Kohn-Sham. So virtual orbitals are anyway necessary. And yeah, actually your question was important because DFT people don't use CI, no? So that's why they don't realize virtual orbitals, except for ionization, electron affinity, only for electron extended Koopman's approximation and all that. Janak's theorem.
The reason could be that you are now actually calculating from a local potential.
Yes.
Therefore, the completeness, orthogonality, etc. are far superior. when
Yes,
you
yes.
are-
So yeah. Yeah, so. No, Hartree-Fock will be good. Yeah, so Koopman's theorem, not exact, but there's a lot of cancellation. Relaxation and correlation cancellation. DFT, what will happen is that the relaxation and correlation are all jumbled up. So that error cancellation that is happening systematically does not happen in DFT. So it's very hard to say in DFT. So I think, the basis, I am taking a separate NPTEL plus workshop this August on basis sets and functionals in DFT. How both of them can become, I'm DFT again, because I have seen that if I do basis sets and functional in ab initio theory, it will be less popular. If it is DFT, then it will be more popular. So that is for a different reason. So those who are interested may join. The announcement will come very soon on the flyer. So I will discuss a lot about basis set, yes.
It's a one-day workshop.
It's a 10-hour maximum, so 2 days, Saturday, Sunday. Or if it is 6 hours, 3 hours Saturday, 3 hours Sunday, something like that. Yeah. 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 Possible, yeah. More orbital, yes.
So if it was possible, whatever we need, that much amount of time, then that
Ah, gone.
would be treated.
Yeah. No LUMO will be there. So it's bad. It is bad, na? That's why you don't do. Don't do it. First of all, the results will be bad. Because how will you get 5 even for methane? You have to take all 5 from carbon or 1 from carbon. That's bad. So anyway, it is bad. Plus, you will not get any unoccupied orbital. Unoccupied orbitals are very important. You will realize that more in the ab initio theory. Right. Yeah, this is specific about a code, I think. I will not comment on that. But anyway, the codes are codes. So yeah, who else was asking? Yes.
Sir, back when you wrote LCAO, you mentioned overlap between orbitals and everything. Described it as Root-Hans method.
Yeah, Rutham got it.
So, were you talking about slated orbitals or were you talking about the basis?
Any orbital, doesn't matter. Yes, slated orbital. They are AOs. How? Yes. We never write this equation in terms of Gaussian. Gaussian, the expansion of AO to Gaussian is predetermined. So with those Gaussians, I form a AO, I use AOs only in the calculations. Ruthan equation only uses AOs.
For example, say if I am to describe, I just wish to inquire about the orthogonality of AOs. Are they not orthogonal?
They are not orthogonal. They are not orthogonal, yeah.
For example, there are 2 hydrogen atoms separated apart.
Yeah, they are not orthogonal, right. But when I do the MO calculation, I told you that I will orthogonalize them. That is the important part. No? So while calculation, it will become orthogonalized and eigenvalue equation. But the AOs themselves, to start with, are not orthogonal.
So even if there are well separated hydrogen atoms,
Yes.
when we say that these electrons are independent, we say within the approximation that the overlap.
Yes, in fact, if you do Hartree-Fock for H2, that is a very good question. H2 will not separate properly. H2 will not become hydrogen plus hydrogen. If you do MO theory. Valence bond it will. Because valence bond we are actually writing it the way the chemistry dictates. But if you simply do RHF, hydrogen molecule, you will become, this is the line of H plus A, this will go like this. Shoot. The reason being at the distance where hydrogen has separated, the RHF is not the proper description because they are still trying to do spin pair. So their spins remain paired. But at hydrogen plus hydrogen spins don't have any correlation.
No, but simpler person will say, see hydrogen, you have one sigma C and you have one sigma C. And very large distance, they are almost degenerate.
Yeah, that is the problem.
Now very simple, you apply Hund's rule of maximum spin multiplicity, you have two electrons.
So they will become like parallel.
So if they are very close in energy, so they will try to be
Right.
So that brings in correlation. But in nuclear, you don't have correlation. Very simple. So you go to long distance, you see two of those states.
So I said what Hartree-Fock cannot do, and it cannot describe instantaneous repulsion. Now I want to describe this instantaneous repulsion. This is something that Professor Harbola showed in the morning, 2 particles in a box. I'm sorry about the slide; it has gone here and there. But the point is that they cannot take instantaneous repulsion, because what Hartree-Fock potential is doing is having 1 by R12 have a Coulomb and exchange potential, but that is basically an averaging. So it means if you look at the Coulomb, as if the first electron is static, the second electron is moving around that, the density, whatever. The first electron is not moving, that cannot happen, right? Because they are instantaneously moving. So that is why I am calling not repulsion, I am calling instantaneous repulsion cannot be described by Hartree-Fock. Repulsion in an average way I am describing. So what is missing is instantaneous repulsion, and that is the effect of the electron correlation, which goes beyond any mean field theory. The DFT brings it in a very different way, you have already seen. It puts it in the potential, and that is very, very important to understand how DFT does. In the ab initio theory, we are not seeing in this manner. So how to do that? We say that the Hartree-Fock itself was a bad wave function, because single particle is not the exact wave function, single determinant. Just like an orbital is described as a combination of orbitals, actual wave function is a combination of determinants. And how do you get combination of determinants? By replacing one occupied orbital by virtual orbital, or 2 occupied orbitals as 2 virtual orbitals. And that brings in the idea of configuration interaction. So it means, I am just writing in a simple way, that let's say I have a Hartree-Fock, which I now do like this, with a hat phi 0, and I mix with that with some coefficient, I will write the coefficient, where the spin orbital I has been replaced by spin orbital A, where A is virtual, I is occupied. So that's my nomenclature, and I call this CIA, IA. So I is virtual, I is occupied, A is virtual. This is Hartree-Fock. Then this becomes the first configuration interaction. Now you see, to do that, I had to bring in virtual orbital A. This is not a good CI. This will be called CIS. For obvious reason, configuration interaction singles. If you bring in, along with this, if you bring in doubles, so phi IJAB, CIJAB, these are just the coefficients, I less than J, A less than B, this will become CISD, then this will become CISD, this whole thing. And so on. I can keep on building more and more determinants up to exciting all the n electrons. That will become what is called full CI. Within that basis set, interestingly, that is exact. Within that basis set. Of course, if you increase basis set, things will increase because virtual orbitals are increasing. These phi I is a determinant. These are molecular orbitals. These are molecular orbitals, but this is a determinant. A determinant constructed out of Hartree-Fock determinant by changing one column of chi I with chi A. So for example, I have a 2 electron determinant, chi 1, chi 1 1, chi 2 1, chi 1 2, chi 2 2. Okay. Now I am constructing another determinant which is just chi 1 here, but this becomes chi 3 chi 3, for example. Then what is this determinant? I have a 2 electron system, so I have only chi1 and chi2. This is my Hartree-Fock. Correct? This is my virtual orbital. So I have generated this determinant by lifting 1 electron from chi2 to chi3, and I am calling this phi 2 to 3. Correct. That is the notation, just for telling. Yeah.
So if we have a determinant, stator determinant, and we say we are doing Hartree-Fock, and so we take its expectation with the true Hamiltonian.
Always, always. Hartree-Fock energy is true Hamiltonian, yes.
So if say we have a combination of determinants, and if we take their expectation with the true Hamiltonian, so the first Hamiltonian say the basic
Hartree-Fock, that will give you Hartree-Fock energy.
it will give the lowest energy.
Hartree-Fock energy, not lowest.
Hartree-Fock energy.
Huh.
And
Don't call lowest now. Now I am talking for the ground state only. Everything is for lowest energy.
so and the other Hamiltonians,
Other terms,
other terms,
there will be corrections.
other determinants.
They will be all going into correlation.
So they will won't they all give slightly higher energy? And
What do you mean by higher energy? No. That is you are always thinking that my ground state is Hartree-Fock. My ground state is not Hartree-Fock. This is the first thing that you have to remove. Hartree-Fock was an approximation to the ground state.
perhaps you are considering because you are bringing in virtual orbitals, they are of higher energy.
No. Huh.
So the energy will go higher.
No, so the point that I am trying to say that even the ground state psi has to be expanded like this. Because now this is a very important question, a single determinant can never be an exact wave function for an interacting Hamiltonian. So get this out of your mind. That might have come because of the Kohn-Sham thing, but Kohn-Sham does it in a very different way by bringing in exchange correlation potential. But the way we are doing, no single determinant can be an exact state for even ground state, unless it's non-interacting. So these are not excited states. That's what these are excited states with respect to Hartree-Fock, excited determinants, but they contribute to the ground state energy.
May I ask for one more
Yes.
question? So is there no additional interaction we prescribe between say two determinants?
Yes, of course.
So if we do prescribe some form of interaction, are we not changing the Hamiltonian?
No. So there will be interaction energy, for example, between these two determinants. So H here. There will be one integral between these two determinants. There will be another integral between this determinant with H itself. So all of that will come into the energy, except for the Hartree-Fock energy. That is anyway phi naught H phi naught, right? So after that, because of this expansion, there will be more terms which will come. All of these will now become correlation energy. So correlation energy I have already seen, whatever is beyond the Hartree-Fock. So my original total energy is now Hartree-Fock energy plus the rest. The rest will do this. Don't even think of excited state. They can at the most be said they are excited determinants at the most with respect to Hartree-Fock. But they are all contributing to the ground state. I am again repeating this. This is very important. However, if you do this expansion, you will not get only one root because there will be a matrix diagonalization problem. So you will get many roots. One of them will be ground state, one of them will be excited state and so on. But each of them will have different contributions. For ground state, beyond Hartree-Fock, whatever is there, I will call it electron correlation energy for the ground state. So that is how correlation energy is defined. Yes.
May I ask?
Yes.
So when we derive Hartree-Fock orbitals, so we take the expectation value of a determinant with the Hamiltonian and we variationally minimize it.
Yes.
And the variational minimum, the best possible,
Yes.
lowest possible energy
In a,
our determinant would be the
Hartree-Fock determinant, right.
So
But that's still not the exact.
that will not be exact. That includes that approximation that it's a determinant. It's a
Yes,
separate
right.
Fine. But so any other determinant with any other orbital
Yes.
should give
Lower energy. That's true than Hartree-Fock. With Hartree-Fock gives you the best, lower means higher energy. Sorry.
Can I just answer this
Huh.
question? Suppose you have a single electron, forget many electron, one electron, and you solve for hydrogen atom, but you take a Gaussian orbit. If you add more and more Gaussian orbitals, energy will go on lower and lower.
Yes. So this is a variation principle. Please remember any other determinant. So if you take only one determinant, this determinant alone, of course this will give higher energy. But I am mixing with Hartree-Fock these determinants. Then it goes down.
Including more from a complete set.
So that's what I say, more the merrier. That is not only for the basis set, even for here. This is not gone. Your point would be right if I am only using such determinants.
In addition, the amplitudes are also there.
No, amplitudes will be again variationally determined, but this will be variationally determined, and they will have a basically eigenvalue equation of the Hamiltonian. I am not going into details, but the point that physically what it means that I am improving the Hartree-Fock because I am adding more. So variation theorem says when you add more functions, things cannot get worse. Right? So things cannot become higher energy, it will only become lower and lower. So that is a very important part of a linear variation method. This was actually, in fact, all the different roots will also have an upper bound. In fact, this was shown by MacDonald. A very interesting theorem is there. It's called interleaving theorem for the linear variation. Nonlinear variation, you don't have excited state upper bound. So you have only, for the CI, you can have an upper bound for the excited state. So not only ground state, even excited states will have an upper bound, but they will have different values. So basically what will happen, I will have a Hamiltonian matrix among these determinants. Then I will have a matrix of Hamiltonian, I will diagonalize it. Okay, I will get roots. The lowest root will be the ground state, but each of them has combination of all these determinants, each of them. But within that, I have a ground state, I have a first excited state, I have a second excited state. And each of them will be upper bound to their true values. This is very interesting about linear variation alone. So linear variation, see variation method itself is a full lecture. Huh? Please, in the classroom, 3-4 lectures, at least you have to read. A normal variation and linear variation. As soon as you have a nonlinear variation, the excited state upper bound is gone. The normal upper bound for ground state will remain anyway. The excited state, that is exactly what was discussed. That's why DFT has become more complicated, that there is no excited state DFT. Because DFT, Weinberg and Cohn use the variation method, which applies for ground state. Is it clear? So that is very important. So anyway, that brings us to CI. If you do a perturbative calculation, you can show that this Hartree-Fock determinant is an exact wave function for a new Hamiltonian, which is simply sum of the Fock operator. So if I define a Hamiltonian, not the exact Hamiltonian, but an H0, which is just sum of the Fock operators, then it's a non-interacting Hamiltonian. Then this is an exact wave function. Exact wave function. So it's a very interesting way to look at it. Hartree-Fock is an approximation wave function for the exact Hamiltonian, but an exact wave function for an approximate Hamiltonian, which is H0. How good is that? How good is Hartree-Fock wave function can also be generated from how good is this H0 from H. H minus H0, the people have done this. How good is H0 from H also determines how good is Hartree-Fock from the exact wave function. And that's a very interesting ideas that people have got. But the point that I'm trying to say, if you do this H0, then all of these are actually eigenstates of H0. Ground, excited states and so on. And then you can use the perturbation theory. Start with H0 as the zeroth order Hamiltonian. Perturb the Hamiltonian, you get all perturbative results. So that is the MP2. MP2, MP3, I'm not doing. And final thing will be a complete nonlinear wave function that is called the coupled cluster. I will not go into that, but it has an exponential of an excitation operator acting on a Hartree-Fock. That's a nonlinear variation, so hard to excited state done in different way. And you can do variation, but variation is very complicated. All right, so I think I have more or less given a general rundown. I will not talk about DFT because a lot of things have happened. But the DFT, what I don't like is the fact that they have all these functionals, meta GGA, somebody called zoo of functionals, and hybrid functionals, double hybrid functional. In fact, hybrid uses Hartree-Fock exchange. Double hybrid uses MP2. So if I'm going to do MP2, why not complete the by wave function based method? Why am I going to do DFT? I have never understood this. So using double hybrid, even anyway already you have corrupted the idea of Weinberg and Cohn, right? that energy is a function of rho. And now you are using lots of things. Anyway, that is what is called the Jacob's ladder.
Precisely the way functional way.
Yeah, the same way it is now going. That is what is called the Jacob's ladder. A typical results of accuracy. As you can see, of course, you go up the ladder, you get very good. So I didn't want to talk about DFT, but I had a lot of slides on DFT alone because initially I thought I would give on DFT. But after I heard in the morning a lot of DFT, and you can see even DFT is the same thing. Same atomic orbital, Gaussian, all this is there. You can also do for solids plane wave, that is very important for VASP, those who are going to do VASP. And of course, the limitation of DFT already is discussed. Kinetic energy is a problem because you have a Laplacian operator. So you can't write it in terms of density. Exchange correlation is a problem. And you have incorrect interactions, charge densities go wrong, electrons appear to spread out. So those are some of the problems of DFT. But DFT is otherwise very, very good. I will just end with these slides of history. 1970 is a very important mark. That's why I said before 1970. You can see quickly, starting from Bohr's quantized model, de Broglie, Erwin Schrödinger, Hiller's, Hartree-Fock, I have done this, James and Coolidge. Boyce introduced the Gaussian basis for the first time. In fact, poor Boyce, many people don't remember him, the SF Boyce. He actually did a lot of work, and I'll come back to Boyce. Ruthan published his matrix variation in 1951. Just a shot of what has happened when.
So the first person gave the concept of primitive Gaussian.
Right, Boyce. Absolutely. Popel-Nesbeth equation was for open shell, just like Ruthan was for closed shell. And then Ruthan's extended Hartree-Fock to restricted open cell. 1963, remember 1965, this is a very important part of the history. First black box quantum chemistry program. I don't know how many of you remember, I don't know, I remembered. It is called polyatom. Yeah, polyatom. 1965 is the first black box quantum chemistry program, polyatom. Today you are using Gaussian and all that. The first program came, it was developed by, again, MP Barnett. Many people have forgotten, I want to just show the history. 1970, there's a very interesting thing, Schaefer and Bender successfully refuted Herzberg's assignment of the ground state electronic state of methylene, and that really started the quantum chemistry. People started taking quantum chemistry very seriously, very quickly, this methylene problem, otherwise I will do an injustice to the students. 1960, Foster and Boyce was the first to use Slater orbitals and a CI, configuration interaction, predicted triplet B1 to be the bent ground state geometry with a 129-degree bend, carbon, hydrogen, hydrogen. Having about 24 per kilocalorie per mole energy, lower than singlet A1. So triplet was the lower energy. First time Foster and Boyce showed. 1961, Herzberg did a photoelectron spectroscopy experiment and then said, no, ground state of triplet, ground state is triplet no doubt, but it is linear. It is not bent. I hope you understand. And Herzberg being Herzberg, he was a very famous experimentalist, so nobody could challenge him. 1962, Jordan and Langevin-Higgins completed the discredition of Boyce's work. They showed by empirical theory that the ground state of triplet is indeed linear, but it is empirical theory. It has no meaning. 1965, Popel used CNDO method and then Popel predicted methylene to be bent with about 141.4 degree. Boyce said 129 degree. But they did not challenge Herzberg experiment, saying that this is highly qualitative in nature. This is really like Popel backtracking, because Herzberg was very powerful. Politics was there every time. Yeah, so Herzberg was so powerful that John Popel had not got Nobel Prize that time, so he did not challenge Herzberg. But he got bent. 1970, Bender and Schaefer, Henry Schaefer, he became very famous with this. They made the most extensive CI calculation and predicted triplet methylene to be the ground state with 135 degree. Not 141, not 120, but it is bent. 1970, Bernheim and colleagues made an ESR spectrum of C. This is an experiment of CH2 in xenon matrix, 4.2 Kelvin, and concluded slightly bent structure, but they did not contradict Herzberg, saying that that was a gas phase structure. This is in the xenon matrix. So I don't think Herzberg is necessarily wrong. So nobody has challenged Herzberg. November 1970, it is moving fast. Wasserman group reported a second ESR spectrum and again predicted that the bent triplet with an angle between 128 to 143 is the most probable value being 136. right on what Schaefer had done. Second ESR experiment from Bernheim group predicted bend structure is 137. When everybody now started saying, Herzberg reinterpreted his experiment and concluded that it is bent after 10 years, in line with all the ab initio calculation in ESR. It is so unfair. 10 years after, Herzberg said, my data collection was right. All this happens even that time. But I missed a line of interpretation, because they used to interpret. I did not even think of this interpretation, that it could be bent, and he completely missed it. So 1970 is a watershed mark of quantum chemistry, and things started happening very, very quickly. CI, MCSA, perturbation, coupled cluster came in 1966, landmark paper by Zizek and Paldus. Those who are interested should read this Journal of Chemical Physics. 19. DFT came at the same time. Don't forget, Weinberg-Kohn theorem, 1965. And of course, these are ab initio. These are ab initio theories. And post-1970, CC method became very, very interesting. As somebody said, it has become the gold standard, I think, Edison. It became, CCSD triples became gold standard of quantum chemistry. So even today, when DFT people do, they actually look at the CCSDT as a benchmark values. So there are so many plethora of methods. Just like DFT has a slew of functional, we have also several methods. Probably not as many as these functionals, but we also have number of methods. As you can see, CAS-CA, CAS-SCF, CAS-CI. Many of you do this. CAS-PT2, so many of them. Full CI is, of course, the best, and so on. So I'm not going to talk of coupled cluster, but coupled cluster became very, very important, and computers became extremely important. I end with my experience in early days. I don't know how others feel. Lot of excitement that time in doing theory. I don't know whether now people are finding excited to do theory. We are very excited to do formal developments, but there are very few theorists, even globally, who are working. In India, only a handful, but they are all excellent people who are devoted to developments, either ab initio or DFT. I've said. Coupled cluster, of course, beginning to be recognized as a field where new developments were taking place. So I think we are all there, and today,
most of the programs, computer programs, not written, indigenous programs, not written by computer scientists.
True.
They are written by so-called theorists.
True, theoreticians. But theoreticians have to write their own program, because if you have something now, who will beat your drum? If you have a drum, I always say you have to beat your own drums first. And that is what is happening. Anyway, so I think that's about it. So this is the end of my slide. Just to tell you, it will be very unfair if I don't show any slide on coupled cluster. So, because people always kind of brand me as a coupled cluster person. But to come to coupled cluster, you can see how much you have to traverse, how much things. So this is coupled cluster. The Hartree-Fock. The Hartree-Fock, if you look at CI, it was also excitation operators, single, doubles, but 1 plus linear. In coupled cluster, it is exponential. So you have linear square, quadratic square, cube, so double square and all that. So that makes it very, very interesting. And the way we solve it is like a similarity transformation. We get the correlation energy, so it is not variational. The variational has a lot of problems. I didn't want to come to that. This is called similarity transform, and this particular thing has a very interesting, what is called the Baker-Hausdorff expansion. Many of you, those who are interested in mathematics of operators, so those who are interested in mathematics of operators, look at that first thing. This can be derived. Any e to the minus a, b, e to the a, is b plus ba, 1 by 2 factorial, ba, 1 by 3 factorial, ba, and so on. So this is called Campbell. So this really makes it easy. Because of that, you have a very famous size extensivity and size consistency, where the reference separates, the whole function also separates. So that's why coupled cluster is very important. There are so much of coupled cluster. This is just the beginning. My career has gone in coupled cluster, which I didn't talk of. And so thank you very much for your patient hearing. Thank you. And I hope I've been able to place you the DFT. I wanted to tell only one last thing. There is a theory called density matrix theory. One should read this. It's an exact theory. If you have a 1 electron density matrix and 2 electron density matrix, you can get exact energy. because Hamiltonian is only 1 and 2 particle. If you write the 1 particle density matrix, you will see that this can be written in terms of just function of R if you take only the diagonal part, but not the off diagonal part. But they come. Yeah, I hope. I missed it. I was changing my hotel. And the 2 particle density matrix cannot be written also as a product of 1 particle density matrix. There is something else. It can be written provided the wave function is single determinant, but not otherwise. And that is the agony of DFT. If that could have been done, then DFT would have been exact, because density matrix is exact. But we can't do that. I wanted to show that in the board, but now time is over. But 2 electron density matrix cannot be written. It can be written as a determinant of 2 densities only if the function is non-interacting. And that is why the problem of DFT, otherwise things would have been exact. Density matrix incidentally is exact. Please read McQueenie and Sutcliffe, a very famous book on density matrix theory. A fantastic book, McQueenie and Sutcliffe. You learn. Davidson came later. McQueenie, 1960s or 50s. I don't.
Density matrices.
Reduced density. McQueenie has done it.
I request Professor.
I request all of
to say
you.
a few words about it.
Yes, please.
Professor Kohn.
About Professor Kohn, yes. We'd like to hear from you.